Hi everyone, my name is Artur Balanuta and I'm a PhD student at Carnegie Mellon University and Instituto Superior Técnico. Today I'm going to talk to you about my work titled A Cloud Optimized Link Layer for Low Power Wide Area Networks. This was a joint collaboration with my colleagues Nuno Pereira, Swarun Kumar and Anthony Rowe. Low power wide area networks, or LP-WANs for short, have seen a huge adoption as the communication platform for the Internet of Things. Today, multiple LP-WAN standards have emerged, such as LoRa, Sigfox from the industry, and NB-IoT and LTE-MTC from the 3GPP standards organization. In this talk, I want to share some experiences from our large university LoRa deployment, which is an LP-WAN technology that has attracted much research attention in the recent years. LoRa is a long-range wireless connectivity solution that allows extremely low-power devices with 10-year battery life to connect to base stations up to 2 kilometers away in urban spaces. What is exciting about LoRa is its ability to have thousands of devices connected per gateway on the licensed spectrum, in effect creating a potentially ubiquitous connectivity network for the Internet of Things. In fact, LoRa has been widely adopted across the world. For example, these are the locations of active TTN LoRa gateways in the Netherlands. We can already see a high density in most cities. Comcast has been the turning point for LoRa in the US since they announced the integration of LoRa into their set-top boxes to enable smart home applications. Suddenly, LoRa has shifted from being a sparse deployment with a couple of gateways per kilometer to now have several base stations in just one building. This trend of massive gateway deployments motivates a fundamental rethink of LoRa's medium access control. In particular, LoRa's link layer was really designed to be simple in operation, and the wireless link is assumed to be between a LoRa client and a single gateway. In other words, LoRa is not ready to take advantage of this new opportunity that comes from having many gateways receiving the same packet at different locations. In the rest of this talk, I will show you how designing a one-to-many link layer can help significantly improve the performance of LoRa. We introduce OPR, which stands for Opportunistic Packet Recovery. OPR is a new LoRa link layer protocol that is explicitly designed for multi-gateway deployments. OPR's key innovation is an approach that allows to decode LoRa packets that are not recoverable by any one gateway, but can be correctly obtained by collectively looking at the data received from multiple gateways. We deploy OPR on a wide area testbed in the city of Pittsburgh, centered around the CMU campus, and our system shows significant improvements in packet recovery. To better understand how OPR works, let's start by looking at where the traditional link layer fails. Let's consider the following network topology where a LoRa client is in range of 3 gateways, one with where the connection is strong, and 2 others where the connection is weak or experiencing some kind of interference. So let's say the same message sent by this transmitter is received correctly at the first gateway, but is received incorrectly at the other 2, which in traditional LoRa means that the message has failed the CRC validation at those gateways. The correctly validated packets are then forwarded to the server in the cloud, and then the packets that are marked as damaged are locally discarded. This brings us to the failure mode of traditional LoRa. In case all LoRa gateways are either in a zone with lots of interference or the received signal is very weak, then in this case we'll experience a packet loss. I want to emphasize that this is not a rare event. Our experience on a large-scale testbed in Pittsburgh shows that this happens very often. In fact, in some gateways, CRC failures occur as much as in 50% of the packets. The usual suspect, of course, is interference from co-located networks, because unlicensed sub-GHz ISM bands are getting more and more crowded. But other factors such as noise and signal multipath also play a big role. So in OPR, we looked at this situation and thought in examining what was really happening. Can we somehow repair these drop packets who failed the CRC validation? To answer this question, let's have a closer look at these 2 broken packets. When compared with the original packet, we know these errors are often across a small number of bits, as shown here by the red segments. What's more important is that the same transmission, these red segments are not always in the same position across all gateways. This is unsurprising and comes from the fact that different gateways are at spatially diverse locations. This means that they are likely to experience interference from different sources. In addition, all other effects like attenuation, multipath, and receiver attributes are usually different at each receiving gateway. As a result, this leads to an even more variations in the positions of the error regions inside a packet. Inspired by these observations, our system explored these erroneous packets that we call fragments to an OPR server in the cloud. The OPR server then exploits this spatial diversity to reconcile the different packets, find the errors, and correct them. After which, the corrected packets are then sent to the LoRa servers as if the packet were correctly received by the gateway. So what does OPR actually do to recover from these errors? I'm going to present a simplified view of our approach, and you can read our paper for further details. Remember that OPR's inputs are many fragments of the same packet that have failed the CRC validation, and our goal is to find the correct packet without errors. I'm now going to show you a series of opportunities that OPR exploits in making these corrections, most of which can be combined in order to improve OPR's performance. The first and perhaps the obvious start is the majority rule. Let's assume there are a few unique errors scattered across the fragments. If at least 3 copies of the same message are available, then we can apply a simple bitwise majority rule. The resulting packet is likely to have significant fewer or no errors at all. The problem here is we don't actually know what the bit errors are within the packet. We have marked them here as visual cues to exemplify the logic. But what if there are fewer than 3 reliable fragments? One thing we do is compare the fragments with each other and identify the dissimilar regions. This only gives us a rough estimate of the regions that cause the packets to fail. We'll see later how we can use this information. But first, what if we are only able to obtain one signal fragment? Fortunately for us, we explore a feature of commercial LoRa devices where we obtain the RSSI information for the entirety of the received packet, contrary to systems like Wi-Fi where we only get one value for the whole packet. This means that we can directly correlate signs of interference by looking at the RSSI values throughout the packet's reception. As a consequence, we roughly know the regions of the packet where errors are likely to have occurred. But how do we know which of these bits were actually flipped? This leads us to another opportunity. OPR uses checksums within the packet to correct for bit errors. Particularly, we know that LoRaWAN packets have a predefined structure with multiple checksums embedded in the packet, as well as message integrity codes that are usually used for data integrity and message authenticity. We can effectively brute force the bits within the faulty regions in an attempt to pass the CRC and other such integrity checks in order to validate that we have obtained our original packet. By doing so, we're effectively using them as redundant sources of information. Finally, I should also point out here that some bit errors are much easier to correct. For instance, LoRaWAN frame headers are standardized and uplink messages contains a lot of setting information for a particular LoRa network. To make our life easier, LoRaWAN packets have a lot of structure and integrity codes for our system to exploit. There's a large fraction of static data in the header, a 16-bit CRC, and a 32-bit message integrity code. Keep in mind that for a large class of sensor applications, data payloads are very small and these fields can account for a big portion of the packet. So in a nutshell, OPR is what we call a clever brute force of packet chunks that are expected to have errors. We can correct up to 30-bit of errors on commodity servers, and our approach can be easily offloaded to FPGAs for even faster performance. At this point, or perhaps when I said brute force, I know many of you are concerned about the exponential nature of these computations. Can we even brute force this amount of bits in the time we have to reply to a LoRaWAN acknowledgement? The turnaround time for LoRaWAN acknowledgement are extremely lax, 1 or 2 seconds. which is several orders of magnitude higher than we are expected on Wi-Fi and cellular. As we can see here on the graph, this gives us plenty of time for compute. For example, we can even use a Raspberry Pi 4 to compute up to 24-bit of errors under the required threshold. Of course, I presented here a very simplified version of our system, but I encourage you to read the paper for detailed end-to-end system design and various optimizations we used. I want to step back a little and highlight a few key takeaways from OPR. First, this work is part of a series of papers from CMU that shows how LP-WANs should really use the cloud a lot more to improve system performance. Given that the devices here are dumb, low power, and have very relaxed latency requirements, there's a lot of potential to offload computations to the cloud. On the other hand, I want to emphasize that OPR can improve performance for a lot more than just the corner cases I showed you and the battery life savings that comes with avoiding the retransmissions. Here's what I mean. Now that the clients know that OPR exists in the network, we can instruct them to either lower the transmit power or speed up their data rates. This means that they can now save precious battery life in the knowledge that OPR will take care of the rest. Not only that, but this also frees up airtime on the spectrum, which increases the overall capacity. In other words, our approach can benefit all clients and neighborhood networks, not just the ones with bad coverage. We implement OPR on a large outdoor testbed in the city of Pittsburgh. For this, we had to install gateways on rooftops on multiple buildings. We also conduct indoor experiments within a large CMU office building. Our experiments show that OPR scales with an increasing number of gateways, which significantly improve bit error detection in packets. These experiments are focused especially on bad packets that could not be recovered at any single gateway. Across a number of setups, we calculated the number of bit errors received across an increasing number of gateways. As expected, we see a relatively small number of bit errors of less than 20 bits per packet that dominate the distribution and validate the presence of zones that we care about. We also show that this resilience to bit errors also translates to resilience in packet errors. Our results then show that with 6 gateways, represented here by the red line, can recover a substantial fraction of the packets that would otherwise simply be discarded by the gateways. Of course, this curve falls off with more bit errors, but the key takeaway here is that with every salvaged packet helps us avoid retransmission and preserve battery life on the clients. These are just some insights on the performance of OPR, and more details can be found in our paper. Our paper is related to a series of recent works in LP-WANs, mainly at the physical layer in optimizing for collisions, coherent combining, and the various other approaches that can be used to save battery life. In contrast, OPR distinguishes itself by working at the link layer, with the key advantage that it is compatible with existing hardware and can operate as a module independently from the LoRaWAN network itself. In fact, OPR is already running on our LoRaWAN network at CMU. While our current work does not dive into modifying the nature of error-correcting codes of LoRa packets, we believe that developing coding strategies that fully embrace the one-to-many LoRa architecture we discuss here is an exciting area for future work. To conclude, I presented OPR, a system that leverages the cloud for opportunistic packet recovery at the LoRa's link layer. OPR leverages spatial diversity owing to the multiplicity of gateways in the vicinity of LoRa clients, leading to a one-to-many architecture. OPR is readily deployable on today's LoRaWAN systems, recovering packets that would normally be dropped and therefore saving battery life by avoiding retries. We also believe that our approach is an additional degree of freedom that should be used by clients in choosing their data rates. Thank you, and I'll be happy to take any questions.